Hello and welcome to this lecture. So in this lecture, we're going to look at convergence rates for different line search methods, or really just for one particular line search method. So uh, it's of interest to understand not only that a line search method converges, but also how fast it converges. So that's precisely the topic here. Now, unfortunately, the results in this lecture are not as general as the previous ones. So you'll recall previously that we used Zootendijk's theorem to show that the steepest descent and the quasi-Newton methods converge, um, given certain reasonable conditions on the cost function. So these were cast iron guarantees of convergence. So here we're interested in how fast these particular methods converge, but the results are less general. Indeed, we're going to limit ourselves in this lecture to proving a key result about the convergence rate just of the steepest descent method for the model quadratic problem. So we're zooming in on the model quadratic problem. Now, the optimization problems that we're interested in this course, they all resemble the model problem sufficiently close to the minimizer by 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 a Taylor approximation. So this specialization in the lecture does not really involve much loss of generality. So we look at section 6.2, and we're going to prove a result about the convergence rate for the steepest descent method, looking at the quadratic cost function f, which is a constant, plus a dotted with x, plus a half times x dotted with b times x. So x is our variable, a is a constant vector, and b is a symmetric positive definite matrix. And we're looking at the descent direction. So that's given by P equals minus grad F, which is minus B times X. And you can see just for this particular presentation of the steepest descent method, we're going to bundle up all of the information about the step size into alpha K. So we're not actually normalizing the descent direction here, which is fine, because that information will be contained in alpha K. So the update step then is xk plus 1 equals xk minus alpha k times grad f. And that's xk, well, that's the same thing again there. So we now need to choose alpha k. So alpha k minimizes f at xk minus alpha xk. So of all the steps, sizes to choose, you choose the one that minimizes f the most in going from one step to the next. And the minimizer is taken over alpha positive because the direction is already fixed as minus grad f. And for the model problem, there's actually an analytical solution for alpha k, which I present here. And we will also look at this more later on. We're just going to take this as given for the time being. And this is actually a key result that we will come back to later in the lecture. So we're interested in how fast the method converges. So it will be of interest to know how far we are from the true minimizer at iteration k plus 1, and how far we are from the true minimizer at iteration k. And the difference between these two is alpha k grad f. And that's just obtained by subtracting x star from both sides of the update step. So this is a key expression, and yeah, it's telling us how much closer we get to the minimizer in going from one update step to the next. And yeah, this is going to be the key expression that gives us the convergence rate. And we multiply this expression across by b, so we get b into xk plus 1 minus x star is equal to b into xk minus x star minus alpha k times b grad f. And I now take the dot product of both sides with xk plus 1 minus x star. So on the left-hand side, it's xk plus 1 minus x star dotted with b into xk plus 1 minus x star. And that's again xk plus 1 minus x star. And this particular combination here, I replace with b into xk minus x star minus alpha k times b grad f. And this particular combination I write as xk plus 1 minus x star b squared. It's not quite a norm. Well, it is a norm, but it's not the usual Euclidean norm. Because, okay, I'm taking the dot product of this vector with itself, but then b is a weight. And we'll actually come back to this in a minute, but suffice to say for now, we're just using this notation in the red to denote this particular dot product. So the next step is to expand this out. So my xk plus 1 minus x star b squared is equal to this xk minus x star minus alpha k grad fk, because again, that's from the update step. And then this is dotted with b times the same thing. So I expand out, and there are 4 terms, which I've indicated here. So expanding out, the first term will be xk minus x star dotted with b times xk minus x star. And then the second term will be alpha k dot times xk minus x star dotted with b grad fk. Then the next term will be minus alpha k grad fk dotted with b into xk minus x star. And finally, alpha k squared grad f dotted with b grad f. And the first term here, I note it's that combination again of xk minus x star dotted with itself and weighted with b. So this is xk minus x star b squared. Okay, so I just gather everything up. So I've got the xk plus 1 minus x star b squared is equal to xk minus x star times the b times xk minus x star, then minus the alpha k xk minus x star b grad f, minus the same thing again, and then plus alpha k squared grad f scalar product with b grad f. So what I'm doing here, actually kind of skipped over it a little bit. Going back up, I have the b here, and it's actually a symmetric matrix, so I can bring it over, and it's a b acting on grad f, and this is because the dot product is symmetric. This will be xk minus x star b grad f. And that's what I have down here. So the point then is that this is the same term appearing twice. And I can only really do this manipulation because B is a symmetric matrix. So that means I have the same term appearing twice. So it's the minus 2 alpha k. Yeah, so I now return to what I mentioned a few minutes ago, that I identify this weighted norm. So the B norm of V squared is the scalar product of V with B times V. And this is for all V in Rn. And this is a norm because it's greater than or equal to 0. And the only way for this norm to be 0 is if V itself is 0. And this comes from the fact that B is a positive definite matrix. So this is the definition of a norm. That the only way for this thing to be 0 is if the vector itself is 0. And this again only works, you can only construct a weighted norm like this when the weight matrix in question is positive definite. So we can really refer to this scalar product combination as a norm. It's the B norm. So going back to what we had previously, I've got xk plus 1 minus x star in the B norm squared is equal to xk minus x star in the B norm squared. And then minus the the corrections, 2 alpha k, then the scalar product of xk minus x star with b grad f plus alpha k squared, scalar product of grad f with b grad f. Okay, and I just rearrange this slightly, so I will take the xk minus x star over to the left. And so now I have the difference in the B norms, xk plus 1 minus x star in the B norm squared, minus xk minus x star in the B norm squared is equal to things on the right-hand side. And it's just, there's no obvious reason to do this, but it's just where the calculation goes. I multiply across by -1. So then I have xk minus x star in the B norm squared minus xk plus 1 minus x star in the B norm squared is equal to pluses on the right-hand side now. So 2 alpha k times this scalar product minus alpha k squared times grad f scalar product of b times grad f. And this particular combination on the left-hand side is going to be interesting. And that's what we work with for the next part of the calculation. So I call it delta. So delta is now everything that was on the right-hand side. So it's the 2 alpha k times this particular scalar product minus alpha k squared grad f b scalar product with b grad f. So the aim of the next part of the calculation is to simplify this expression for delta as much as possible and to make it into something recognizable that only really involves b and a and so on. And to do that, I use the fact that we're working on the model problem. So grad f for the model problem is a plus b times x. But b times x star is minus a. That's the minimizer of the model problem. So grad f is really minus bx star plus bxk. Or this nice expression, again, only valid for the model problem, grad f is b into xk minus x star. Okay, and I sub this back into delta. So delta is 2 alpha k times the scalar product of xk minus x star with b grad f minus alpha k squared grad f scalar product with b grad f. And I again use that trick we had before that B is a symmetric matrix, so it can act on the left. So now delta is 2 alpha k times B times xk minus x star scalar product with grad f. So grad f is appearing by itself now. It's no longer multiplied by B. Minus alpha k squared times grad f scalar product with B grad f. So I now also use the fact that B times xk minus x star is grad f for the model problem. So this expression for delta becomes 2 alpha k grad f scalar product with grad f. That's this guy. And then minus alpha k squared grad f scalar product with b grad f. Okay, so this is what I have for delta. And the next step is to fill in for the optimal value of alpha k, which I stated previously, and it's known exactly for the model problem. So delta is 2 alpha k, and I fill in here the analytical expression for alpha k times grad f scalar product with grad f, and then minus alpha k squared. So it's alpha k times alpha k. So this is the analytical expression times grad f scalar product with b grad f. But now I get a cancellation because downstairs I have grad f scalar product with b grad f, and upstairs I have grad f scalar product with b grad f. So this then it's the same term that appears twice. So I've got 2 times something minus 1 times something. So overall delta is grad f scalar product with grad f squared. So that's this guy times that guy. And then divided by grad f scalar product with b grad f. So this is my expression for delta. And now I remind myself what delta is. It's the b norm of xk minus x star squared minus the norm of xk plus 1 minus x star squared. And this is delta, which is grad f scalar product with grad f squared, divided by grad f scalar product with b grad f. And I just rearrange. So I take the xk plus 1 over to the right, and I take the combination of dot products over to the left, and I just rewrite this like so, and this is my key result. I'm really on the home straight now because I now have the b norm of xk plus 1 minus x star squared is equal to the b norm of xk minus x star squared minus a correction. So this is telling me in going from one iteration to the next, my difference between the minimizer and my guess gets smaller and gets smaller by this amount here. So this is a great improvement, and the aim of the final part of the calculation is to find some nice expression for this correction. And the first step in this final calculation is to take the correction and to multiply it by 1. So in other words, to do nothing. And 1 is the same thing as xk minus x star in the b norm squared upstairs, divided by the same thing downstairs. So that looks like nothing, but there's a strategy here, which is then to identify a common factor and to take that outside. So the common factor now is xk minus x star in the b norm squared into 1 minus grad f scalar product with grad f squared over grad f scalar product with b grad f times 1 over the b norm of xk minus x star squared. And this is a very nice result now, because it's saying that the difference between my updated guess and my minimizer squared is equal to the difference between my previous guess and the minimizer squared times a multiplicative factor, which is less than 1. So the difference is shrinking at each iteration. And it remains now just to find a nice expression for the shrinkage, so I can say something precise about the convergence rate. So to make this last expression a bit nicer, I go back to the quadratic model problem, where grad f is equal to b into xk minus x star. And I take a matrix inverse on both sides, and I can do that because this is an invertible matrix with all positive eigenvalues. So b to the minus 1 times grad f is xk minus x star. So the b norm squared of xk minus x star, by definition, is the scalar product of the vector xk minus x star with the vector again, weighted by b. But I now fill in for xk minus x star, which is b to the minus 1 grad f. And I therefore get some cancellations so that the b norm squared of xk minus x star squared is grad f scalar product with b to the minus 1 grad f. So I then go back to this expression and I sub in for the b norm of xk minus x star squared. So the b norm of xk plus 1 minus x star squared is equal to the b norm of xk minus x star squared into 1 minus what I had before, grad f scalar product with grad f, over grad f scalar product with b grad f, and then I have the grad f times b to the minus 1 grad f. And then I've just rewritten the square as 2 copies of grad f scalar product with grad f. And there's a reason for doing that, which we now come to. So I want to look at this particular combination. So this term, and then turn it upside down. So I want to look at grad f scalar product with b grad f normalized by grad f scalar product with grad f. So in other words, some vector, let's call it, I don't know, w, b, w over. So this will be the same thing as a unit vector scalar product with b times a unit vector. And it's some unit vector. And I do the same game for b to the minus 1. So I'm looking at the scalar product of some vector grad f with b to the minus 1 grad f normalized with the scalar product of grad f with itself. And this would be less than or equal to the max over all unit vectors, which is precisely the matrix norm. So up here, this is less than or equal to the matrix norm of b, and then the same thing for the matrix norm of b to the minus 1. And this is exactly, you remember, the condition number. And another way to write the condition number is lambda max over lambda min for a positive definite matrix. So I have this inequality that this left-hand side is less than or equal to kappa b. And now we just have to be careful with all of the directions of our inequalities, because going back up to this previous expression, it's 1 over this. So whereas before the inequality was less than or equal, we're inverting, so now it's greater than or equal to 1 over kappa b, the condition number. But if I were now to multiply both sides by minus 1, the direction of the inequality reverses again. And if I add 1 to both sides, the direction of the inequality is again less than or equal to. So, going back up to this expression, I have the b norm squared of xk plus 1 minus x star is equal to the b norm of xk minus x star squared times 1 minus 1 over this combination of inner products. And now I've worked out carefully that this is less than or equal to the b norm squared times 1 minus 1 over the condition number. And 1 over the condition number is lambda min over lambda max. And I just take a common denominator. And happily, you know, for consistency, this is positive. And this gives me my final result. I just take square roots. So the B norm of xk plus 1 minus x star is less than or equal to the B norm of xk minus x star times this shrinkage factor. And the shrinkage factor is lambda max minus lambda min over lambda max to the half. So this is our key result that we've shown. So this is the convergence rate of the steepest descent method, and it's called a linear convergence rate. Because the difference between our updated guess, albeit in the B norm, is less than or equal to the difference to some power times some multiplicative factor. And the fact that it's linear convergence means the power is 1. Now, in a later lecture, we'll see for the quasi-Newton methods that A is 2, and that would be quadratic convergence. But here we have linear convergence, a linear convergence rate, because the power in this final expression is A equals 1. And we just make a comment in passing where things can go wrong with the steepest descent method. And it goes back to the condition number. So if the condition number is very large, then there's a very big separation between the maximum eigenvalue and the minimum eigenvalue. In which case, this ratio, lambda max minus lambda min over lambda max, is always strictly less than 1, but it's tending towards 1. So then this shrinkage factor is tending to 1 as well. So in going from the previous iteration to the next, you don't get any shrinkage at all, or if you do, it's very, very small. And that means in such a case that the convergence is very slow. You're getting very small shrinkage with each iteration, so you're going to have to do thousands or tens of thousands of iterations to get to a converged minimizer. And this happens when the condition number is large. So the steepest descent method is very poor when you're working with ill-conditioned matrices. And a geometric way of looking at this is that when the condition number is large, the eigenvalues, the maximum eigenvalue is much greater than the minimum eigenvalue. And in some hyperspace, the level set, so the surfaces of constant f, are ellipsoids. And in fact, the ellipsoids are very elongated. So, you know, if it were a 2D problem, the level sets will be ellipses. And the steepest descent method, you might be at some xk, and then you go along the direction of steepest descent, and you go out here to xk plus 1, and then you go again and again. So each time you're doing this kind of zigzag pattern, and you're zigzagging towards the minimizer instead of going directly to the minimizer. So if you go directly to the minimizer, you take very few steps. If you do the zigzag, it takes very many steps. So it's in this kind of example that the steepest descent method gives very poor convergence. And that is enough for today.